Yeah, so then let's start. So our today's speaker is Thibaut Kouptchinsky. So he's now in Vienna. So, right. So yeah.
Right. Yeah. So thank you, Fedor, for also inviting me to talk here in Ghent. I'm in Belgium, where I did my master thesis in the subject I will talk about today. So I just started my PhD, and so yeah. I'm also maybe complete. I'm PhD student of Juan Aguilera, and I work on determinacy axioms in second order arithmetic and beyond. So, first of all, what I want to talk about today is reverse mathematics. I think you are all quite familiar with that subject, since many of you do a bit of reverse mathematics, but I will still remind the basics to begin slowly. Let's say, is it okay? Can you see well if I write like that?
Yes. Well, you have also to be careful because you're making a recording, put it on YouTube. So when you explain the basics, it's fine. Also for the people who finally look at the lecture.
Right. So I have to explain the basic carefully. Maybe let's start with a very let's say, a mainstream example of reverse mathematics outside of the usual framework. So if you are working Zermelo and Frankel set theory, and let's say you want to prove Zorn's lemma. So it is not possible, but if you add an extra axiom, namely the axiom of choice, then let's call it Z now, ZL, Zorn lemma, but attached, not the Zermelo lemma. Then you can prove with choice Zorn lemma. And the fact is, concerning Zermelo and Frankel set theory, choice is the right axiom to prove Zorn lemma in the sense of reverse mathematics. Because if now you decide to add Zorn lemma as an axiom to Zermelo and Frankel set theory, you can prove back the axiom of choice. So that will be our criterion to find the right axiom to prove the theorems of mathematics. So that's why reverse mathematics, because we have this second process checking that the axioms are right, that consists in proving back the axioms, which is the reverse way to do maths. Okay, but here in Zermelo and Frankel set theory, we have a very powerful setup. Usually in reverse mathematics, we will always work. All right. Now I understand why I should begin by the front one. We will always work for second order arithmetic. Well, not always, but it turns out, following the works namely of Friedman and Hilbert for arithmetization of mathematics, that most of the theorems of everyday mathematics can be proved in second order arithmetic. So second order arithmetic, I will write it Z2, but you can think of it as ZFC minus for a set axiom. And actually, there are pi 1, Z2 is pi 1 for conservative of that theory. So for not too complex sentence, it is the same, and for our main interest today, it will be the same. But so the idea of restraining the strength of the theory, do not have for a set axiom, for example, is to work more carefully on what axioms are really needed. For example, what axioms are really needed for Gödel's completeness theorem or for Bolzano-Weierstrass theorem. And so I will briefly state what we call the X5 of reverse mathematics, And it turns out that most theorems mathematics can be proved inside 5 subsystems of second order arithmetic. So we begin with a very, like, let's say, base theory. You can think of it as constructive mathematics, and we will label it SE0, so recursive comprehension axiom. So maybe I should briefly sketch what's happening here. So let's think of a model of second order arithmetic. So we have a set of number, a set of subset of number, and then usual function of arithmetic, constants, the order, and the belonging relation. And we will always suppose we have that n is an ordered summing for the function and constant. And that we have a basic induction axiom that I will call I0. So basically, if you have an inductive set in the world of the subset of number, then it is the whole universe, it is the whole n. So every number belongs to this set. So this relation is between these two universe. Okay, and in SE0, what we add is a way to be sure to dispose of some set, the set that we can create constructively. So if we have a property, if you have two properties, phi and psi, that are phi 0, 1, so that has only one universal quantifier on the first order variable, the number variable, and that we can prove that under the axiom, or the axiom phi and not psi are equivalent, so you have a property that is can be both expressed in a phi 01 and sigma 01 way, then it will be in some sense computable, and you can create a set X that contains every number that satisfies this property. Right, so this is the axiom scheme of recursive comprehension. So of course, X could not be a free variable in the formula, but you allow parameter. And so that's the reason why if I want not, so this is called delta 01 comprehension, but if I want sigma 01 comprehension, I have also phi 01 comprehension because I can take complementary. And I can also have every arithmetical formula that I can use as a definition for a set, because then I can build up the hierarchy using the set previously defined as parameter. So we cannot strengthen this system by adding more arithmetic comprehension. However, something that can be non-computable is the existence of infinite paths in some infinite trees, for example. And that's why the second set system is WK0. So for weak Koenig's lemma, it says that if you have an infinite binary tree and it has a branch. So it is a new way to create new sets with strengthening of every integer. Next, you have arithmetical comprehension. That's the axiom scheme of comprehension for every arithmetical formula. Then finite recursion. Let's say you can take any arithmetical property and build a process of recursion on that property, and this will be a new set again. And then finally, the strongest of the big five is phi 1-1 comprehension. So here you allow, in the definition of a set, you allow a universal quantifier on set variables. And here we cannot have the same argument. So the hierarchy is then phi 1-1 comprehension, phi 1-2 comprehension, etc. And it goes until pi1 infinity comprehension, that is set 2 for the second order arithmetic. But most of the theorem of mathematics can be proved inside the 5-2 system. For example, Gödel's completeness theorem can be proved with using only Wilton's lemma, and we can prove that it is the right axiom to prove it under AC0. Here you have completeness. And here you have Bolzano-Weierstrass theorem. But today I want to speak of a very specific kind of theorems. They are called determinacy. You can call them theorems or axioms depending on the point of view. Today we change our point of view very often. So let's call them determinacy axioms. So these axioms are very popular in set theory, for example, to solve questions that are not solvable inside ZFC. Typically measurability question. But today we're going to use, let's say, the baby version of the axiom of determinacy. So basically what we are doing is playing a two-player infinite game of perfect information. So 2-player 1 and 2 play natural numbers in a setting. Alternatively, knowing the moves of the preceding moves that are played, and knowing that the other know also that also have access to this information. And after omega moves, it creates a sequence of natural numbers. And then the goal of the game is to end up in some payoff set. So we have to fix a payoff set in the sequence of omega, or we could restrict the move that we can play to have more complex rules, but we will be only interested in this kind of payoff set. And in the end, when you have enough strong axiom, it does not matter actually what kind of tree you use in the rules of your game. But then if the sequence that form belongs to the payoff set, player 1 wins. Otherwise, player 2 wins. So, and then the question is, so for finite games, we know that always one of both players in a perfect information game has a winning strategy. But here, the question is, does any of both players have a winning strategy? So, but so this question, if we allow every such game to have winning strategy, we end up with a very powerful axiom. And that can prove, for example, that every set of real numbers is Lebesgue measurable, in contradiction with the axiom of choice that can create non-measurable set. So we will be interested in local version of this axiom, and we will only consider some x belonging to some class of definable set. So you have a Borel hierarchy in the Baire space, the Polish space. So you begin with the Kloppen set. Measure 1 are the open set, measure 1 closed set, and so sigma 02 are infinite unions of closed set. Phi02 are infinite intersection of open set, and the delta class are always intersection of sigma and pi class. And it goes on and on until any Borel set, but I will directly write delta 1, then you have the projective set, and it continues then. All right. And the result of mapping is that ZFC proves Borel determinacy. The determinacy is the statement that either one or two has a winning strategy, so that whatever two, for example, if one has a winning strategy, whatever will be the play of two, he will end up in the payoff set by following this strategy, which is a function from the partial position to the next move. Right. But in this proof, we need to unravel games and in order to do that, we really use the porous set axiom. So this and the porous set axiom is necessary to prove delta 1-1 determinacy. So this shows us that Borel determinacy, for example, is not provable in second order arithmetic, but we can prove more tiny version, more weak version of determinacy inside second order arithmetic. For example, the result of Steele, and you can also find in Simpson. And actually the proof of the reverse direction at least by Tanaka, or we just write the three of them, is that under SE0, then prove that delta 0-1 determinacy is equivalent to sigma 0-1 determinacy, and they are equivalent to the axiom of finite recursion. So already the fewest, the first level of the Borel hierarchy for the axiom of determinacy are demanding quite strong axioms in our hierarchy of axioms. So compared to most theorems of mathematics, this one is a powerful one, we say. As powerful as the axiom of constant recursion.
Yes, so what was actually the story about this? So it was first proved by Steele and Simpson, and but so I mean, so not Paul proof, but basically the determinants is proved on ATI0, and on the then it was reversal proved by Tanaka.
So Tanaka, Steele and Simpson, I know their proof of the reverse direction that sigma 0-1 so delta 0-1 determinacy implies the axiom of finite recursion. I would personally recommend more the one of Tanaka, which I find more readable, but it's a question of taste, of course. But I also put Simpson because you can find, well, you can find every classical reverse mathematical result in it. I don't know about the other direction, but ATI0 can prove sigma 0-1 determinacy. I know the proof of Simpson, but I don't know who did that proof first. But that's why I figured that. Depending on the direction you want to run, you can navigate between the
Okay, but yeah, so apparently the first it was proved by Steele.
Right. Okay.
We didn't reconstruct it.
Yeah.
Okay, so okay.
Right. But then, so here these two steps are equivalent, but then it's very steep. So if you increase a little bit the complexity of the payoff set, you need way more strong axiom. And the second theorem, this one from Tanaka and McLean, for example, is that SE0 proves that if you consider determinacy, determinacy with payoff set that are conjunction of a sigma 0-1 set and a pi 0-1 set, then it is equivalent to the axiom of pi 1-1 conjunction, which is of course, well, which is stronger than ATC, way stronger. And then it goes on, and I will talk about even stronger results later. But now I want to take this opportunity to do a little bit reverse mathematics and to show this direction. How from the existence of some winning strategy with this complexity of player set, we can end up by proving pi-1-1 comprehension. Right. So what we need to prove is that taking a formula phi of n of this direction in the pi-1-1 class, we should prove that there exists a set, so that's for n, and that the formula is true. So first, we will use the normal form of a pi-1-1 formula. So let's write it like for function from the natural number to natural number. There exists an initial segment, so that's some recursive relation of n, and this initial segment of the function is true. We can do that because we have one universal quantifier on set variable that we can interpret as function by some coding. And here you may have any arithmetical formula, but the implication of for all there exists, you can put scaling function inside the inside this function. So that's the reason why. But we will use this normal form crucially to be able to define a game, so that if it's a player that should have a winning strategy can use it to define the set X here. Right. So we use so Christian so far. So that's the part that I like about the reverse math of games, is that you have to define clever game to prove these axioms. That's the most exciting part in my opinion. So the game will be played as follows. So first player one will play a natural number n in order to raise the question whether phi of n holds or not. And then player two will answer 0 or 1 if he thinks or she thinks that phi of n holds or not. So, and one will try to contradict her. So, for example, what happens if phi of 2 says phi of n holds? So that means she plays 1. Then, in order to contradict her, 1 should provide a function So one would observe by the fact that there exists a some function such that for all initial segments, the relation does not hold for this n. So the goal of one here is to play this function 0, 1, whatever 2 is played. And so on. But 2 think that phi of n holds. So in his opinion, 1 cannot be right. And at some point, he will find initial segment of the function so that the predicate does hold. So let's say that he can play whatever he wants, but when he wants to stop and to witness that hold, he played 0. So here somewhere. And then at that point, so in that case, 2 wins if this initial segment F0, F1, and the bond when he decided to stop it by playing 0 false. Right? And in the other case, if 2 thinks that the formula is false, it is to him to provide this function. So they switch the rules, and one has to prove it wrong. And if player 2 is right, then one cannot prove it wrong. And you can write this condition as here I wrote a part of the condition. If 2 things that phi of n holds, and he play 1, so either he play 1 or he play 0, and depending on that, the condition is a bit different. But then the winning condition for 2 can be written as either a pi 01 formula or a sigma 01 formula. Well, as a disjunction of such formula. So this means that the winning condition for 1 is as we want it. Conjunction of these 2 kind of formulas. Yeah, so are you convinced, or do you want more details on that formula? So here it's very important to have both formula, because by checking that fall, so if you say that there exists, and then you would put your condition with a conjunction, and everything has to hold, and this is a specific form of the game for 2. But to force player 1 to play this specific form of game so that it has sense to our interpretation, we need the for all condition, because then for 1 it would be an existential condition forcing him to play something specific. I want to vulgarize it. Okay. So this is a really nice example of how the hierarchy, the Borel hierarchy, strengthens very quickly the determinacy axioms, and it can be witnessed in second-order arithmetic. Another example of that is that if you restrict yourself to play binary moves, to yeah, it's not the main point of my talk, but it's also interesting if you restrict yourself to a tree, plain tree inside the binary sequence, then we can consider also delta 0, 1 determinacy in binary trees. So we will witness that by a little star. And this is equivalent to WK0. So it's weaker at this stage because we have not very powerful axiom to do the translation between binary moves and every natural number as move. But also, so this is also equivalent to sigma 1 determinacy in counter space, similarly. And in the same fashion, if you now take conjunction of a sigma 1 and a pi 1 formula as a pair set, but in counter space, then you can end up with full arithmetical comprehension. So something similar is happening if you restrict yourself by playing binary moves. And the argument is quite the same because then you only need to prove pi 1 comprehension, and then you can build up all the arithmetical hierarchy by this by plugging the constant inside your definition of the previously defined. And it's quite the same, but the difference that the game is simpler. All right.
So are there any intermediate levels of determinacy, say, that would be weaker than sigma 1 determinacy, but still non-trivial? So namely, I guess for a particular level, I would be interested in the form of determinacy equivalent to sigma 1 axiom of choice.
Right. So you can. So sigma 1 axiom of choice is weaker than AT0. Between AC0 and AT0. And from sigma 1 determinacy, you have a nice proof of the axiom.
Right, this I know. I was asking whether there is some point that would be equivalent to sigma 1 axiom of choice. Or maybe not. I don't know.
So what was the question?
No. Is there any form of determinacy that
right.
would be below sigma 1 determinacy, or?
I don't know about that. One. So after that, you can build up the hierarchy of sigma 1k formula. So, but it should be well, if it is equivalent to some level of the Borel hierarchy, then it should be, for example, sigma the difference of 3 sigma 1 set in counter space. But I think it is not the case.
Okay, yeah. No, I don't know. So the reason why I ask is because I kind of thinking about this, it like and appears to me that at least in this proofs kind of so establishing reverse mismatch equivalent for weak forms of determinacy, like it really this kind of proofs really feel like it's establishing some kind of choice principle. Oh yeah, but probably it's like as a kind of choice principle, not like sigma 1 AC, but it's like variants of strong choice. So also, I mean, of course, pi 1 comprehension is strong sigma 1. It's equivalent to strong sigma 1 axiom of choice, and it really feels that it's
right.
what you established here. And I mean, like weak Koenig slam is okay. Else it would be regarded as some form of choice, and I guess I don't thought about AC0. Maybe AC0 else in some sense could be thought as some form of choice, but.
Yeah, axiom of choice often play very important roles in the proofs, relying to these determinacy axiom, and especially in the one I will talk just after. Well, even if I won't really speak about them, but
okay. No, I mean, okay. I mean, of course, there is axiom of choice in science theory in this kind of one thing, and there is this kind of choice schemas in second order arithmetic, which kind of, I guess, have a bit different feel to them.
Yes. Here it's always about countable choice, for example, in another arithmetic. Yes.
Okay. Anyway, yeah.
Right. Yeah. I'm just checking about the time, so I think I still have half an hour. Half an hour. So that will be just enough to talk about. Because now that we are familiar with the flavor of reverse mathematics of axiom determinacy, yeah. So I mentioned, so I just erased it, but I mentioned that Martin proved that the DFC, with a crucial use of power set axiom, can prove Borel determinacy. And more precisely, what one can prove, considering the Borel hierarchy, is taking ZFC minus power set axiom, but you still allow to have the distance of the alpha iterated power set of the natural number. Then you cannot prove pi 0 alpha plus 4 determinacy. So these sets are too complex to be used as a payoff set in a game where you want that one of both players, like a winning strategy. But if you take the same theory and add one more iterated power set, then you will be able to prove this version of determinacy. So here we have an inequality for pi 0 alpha plus 4 determinacy in terms of reverse mathematics and proof theoretics. The goal of reverse math is usually to have the perfect bond, well, the perfect equivalent in terms of axiom. Here we only have this inequality, and actually it's not known what is the equivalence of this theorem at that point. But
right, maybe you could give some intuition about how exactly this happens. So maybe okay, so currently basically the smart. Okay, it just proving Borel determinacy, right? It was about this unraveling of
yes,
Borel games. But could you remind me basically from which side kind of you okay? Basically, you kind of what was the deal, right? So you have like pi alpha game, right? On some on some space. And then then you kind of go somehow you reduce complexity of the game by going to space of high cardinality. But my question is from which side you kind of where you actually decrease the index, right? So kind of you decrease from top or from the bottom, or how is that?
right. So from the bottom.
Okay.
So the idea is that we can unravel the open set at the bottom of the hierarchy as Kloppen set.
Okay.
And then all the complexity decreases by one level. Because every infinite intersection of Kloppen is closed, and then it will be an infinite union of closed set instead of sigma 02, instead of pi 02. So
I see. All right, makes sense. Yeah. Right, so because like open, like if you consider say some Borel set is like responding to say like say hyperarithmetical codes or something like that, would be like responding to kind of well-founded tree, right? And we kind of want to recurse on this tree. Yeah, right.
You have a direct proof or a direct without using this technique of unraveling. You have a proof of pi 03 determinacy inside second order arithmetic. But then, if you want pi 04, it's not sufficient. You need one power set. You need the existence of the real number.
Right.
There is no direct proof.
Right, but I guess you actually have something true, because probably you actually put proof inside GFC minus power set pi 03 determinacy for like any space or like any free space or something like that.
Yes, yes, we can do it because
Because I think it's what you want to use in the end, right? If you want like this sharp Martin result, right? Because you kind of want, probably you kind of want to unravel the game until you get it to pi 03 game.
Yeah,
And
yeah,
then
exactly.
you're done.
So yeah, when you translate into the theoretic version, this is less than pi 1/4 sentence, so it's conservative under the C.
No. I think okay. So I mean, if you want to prove like the second result that you mentioned, right?
Yes.
About this pi alpha plus 4 determinacy, then you actually then you would need to deal with spaces that are not bare space, right? So the spaces of extremely high cardinality.
Yeah.
And then you need to prove kind of basically you need to kind of with more general result, right?
But so the proof adapts. So the proof is the same. So it's the same, and here you can play outside the bare space. It depends what you have into.
I get pi 03 and not pi 0.
Yes.
Okay.
Pi 03.
Yeah. Right.
But for example, one question you could ask to sharpen this inequality is: does Z2 prove delta 0 determinacy? Maybe it's weaker than what the term of Martin is talking about, and that was thought to be true until Montalbán and Shaw showed the contrary. So, what did they show? So remember that most of theorems of mathematics are proved, also everyday mathematics or graduate mathematics, let's say, are provable inside these big five, and the strongest of which are pi 1/1 comprehension. Then, so I talk a bit about the difference hierarchy of two sigma 0/1 set for this theorem. Like that, but we can iterate this difference hierarchy, taking the difference of any finite and quasi-finite level of the difference hierarchy for any step of the Boyle hierarchy. So, for example, you know that pi 3. So now you know that you have to trust me, but you know that pi 03 determinacy to go inside second order arithmetic. And what happened now is to consider the difference of n and pi 03. So then, if you first try to prove it inside delta 1 and this 2, comprehension, it does not hold. But what you can show is that pi 1 and plus 2 comprehension can prove this really. So this is the theorem of Montalbán and Shaw. And this shows that, well, if there is a theorem of Kuratowski that shows that if you iterate the difference hierarchy transfinity, you end up with any delta 0/4 set. So this in particular, the corollary shows that the stuff is delta 0/4. Right. So the goal of my master thesis was to generalize that into higher orders arithmetic, following this result of Martin. This result, if you have the existence of more and more iterated power set. So what we are gonna do here is to translate this result into set theoretic ones.
Yeah. But okay, so a question about delta zero for determinacy, so but could we kind of isolate the system so more or less precisely responds to delta zero for the
Yeah, here we do not have tighter bonds yet.
no, okay, yeah, but I don't know, like which means this result, like it shouldn't be that hard, right? So because what you basically have here, right? So we kind of we see that what so this basically levels of difference hierarchy, right? So they kind of corresponds to like levels of comprehension. I mean, I guess then of course like you need kind of all countable levels of comprehension. I guess you probably would want to go to the language of set theory or something like this, right? But this, I don't know. This kind of, I guess it's very easy to formulate a conjecture, right? So I don't know, like that you say, I don't know, that for AC0 plus for any countable ordinals there exists a beta model of like alpha stability, yeah, so something like.
So you mean generalize that to
Oh no, I'm asking about like what would be like reverse symmetric unit of
yeah. Well, I think Juan and Philip, so Juan Aguilera and Philip Bell end up with tighter bonds in this setting, but they didn't find an exact an exact characterization. It's actually it seems to be a quite tough question.
No. I think what Juan and Philip have been doing, they have been like saying kind of precise correspondence of different characters, which yeah, probably is hard. Again, hard like it's not a problem. It's certainly quite subtle problem. But what I have been asking was kind of much more rough problem about what is the reverse semantics of delta zero for the determinacy.
Yeah. Well, I don't know about that.
Okay. Okay.
Yeah, if I understood right. So, yeah, you can characterize that also in terms of level of the constructible hierarchy. When does the winning strategy appear? But actually, in terms of that, these schemes are not the best suited to analyze this kind of determinacy. It's better to compare in terms of existence of vector models.
Yeah.
Right. So here, to have an equivalent version of that statement inside set theory, we will need to use something. So what we can do here is that we can call that alpha order arithmetic. And now we want to restrict the axiom there, so namely the axiom of separation and replacement to stick, to agree with that amount of comprehension. So what we will do is the cryptoplastic set theory. So consists of the basic axiom like pair, union, extensionality, foundation, and then you add the delta zero collection, which is like replacement, but without asking that your set contains exactly the answer to the function, and also that the function does not have to be a function, like one unique weakness. But we will work in constructible universe after that to have this characterization in terms of level, the constructible hierarchy, where these winning strategies for such games exist, and in constructible universe, collection and replacement are equivalent. And you also have delta zero separation. And then that first, then we define KP n. KP for n plus 1, or n plus 1, we can say this was KP1, and then KP n plus 1 is KP1 plus eta n collection and sigma n separation. So that now if you translate these results into a set theoretic characterization of the complexity of determinacy axiom.
I don't know, like the name is really strange to me. Because why we call this system KP? Because I mean, like I think point about usual KP was that kind of collection was in the sense strong with inspiration, right? So kind of in usual KP you have like okay, delta zero collection we feel it's sigma 1 collection, and like but separation is just delta zero separation, don't have sigma 1 separation.
Yeah,
but like when you're naming, like you kind of in a sense your separation is stronger than your collection, right? So
yeah.
okay, I mean, like,
I also feel like
okay,
it should be the contrary, but
I don't
it's well
okay.
this way it would match with the
No, I say would agree with this. Like, I just find it a bit weird to call the system KP because, like, I guess the point about KP was you have to, in a sense, you have your strength was kind of accumulated in Rillian collection principle. Okay, anyway.
Well, for a more general framework, we could rename.
No, I just encourage kind
But
of
here, since we were working the constructible hierarchy,
sure. I mean, okay, no, that's what complain about names.
Yeah, maybe
nothing more. Yeah.
Right. Well, so what we end up with is that if we so the main result about so when you study better models of second order arithmetic, you have this result of Simpson. When I say result of Simpson, it's probably a result of many more mathematicians, but Simpson is like conglomerate of a very big organization.
But you know that actually in that chapter Simpson gives quite accurate historical references. So, I mean, if you kind of actually can take a look there, you will actually learn from other authors of the results. Usually, at this time.
Yes. I don't remember.
Okay. Anyway.
The author of that book. So the minimal find the minimal model of delta 1 and 2 comprehension that we are interested in by considering the model constituted of a set of natural number defined in L alpha n plus 1, where this is defined to be the L alpha n plus 1 with the minimal model of KP n plus 1 KP n plus 1. So also the minimal, in that sense, also the minimal model of delta 1 and student comprehension. Right. So we can say that for all beta, alpha 1 and beta, it's not a model of KP. So the fact is, so it's from the fact that we are working in the constructible hierarchy, we can prove that any model of KP n plus 1 is actually a model of delta n plus 1 separation. Can get a bit more separation, like we had in KP. So in KP, we can prove that we actually have sigma 1 collection and even sigma 1 replacement and delta 1 separation. So here, by using similar arguments, we can show that right. Delta n plus 1 separation. And then if you want to translate formula in set theoretic language, the formula in second order arithmetic, there is one level of the hierarchy of gap. Because to translate, you need to state the existence of a well-founded tree that calls a set. And to state that it's well-founded, you need to have a quantifier, basically. So I also show that it is a model of delta n plus 2 comprehension if you restrict the or the subset of omega that contains. And then the result of non-diagonal short can be reformulated as L alpha n plus L alpha n plus 1 does not prove pi 3 n determinacy, but L alpha n plus 2 does. Is as soon as you have sigma n plus 1 separation, you also have delta n plus 1 base. That is, it's a translation of the result. Right, and so I will keep up with this board because it's more easy. We can continue to look at it, but one. So the results from the master thesis is that we can adapt, so we can define theory KP2 and let's say n for n meter for that one, of course, KP2 and 2 will be KP n plus the real number elements. And similarly, we can define L alpha 2 and to be the minimal level of the same theory. And so this is a preliminary to stating the result. And now the result in itself is that L alpha 2 n does not prove pi 04 and determinacy. Now we are speaking pi 04 determinacy because we have one more concept according to the theorem of Martin. But L alpha 2 n plus 1 is contains the winning strategy of any pi 04 n games. Right. And here we see that compared to the countable case of Montalban Shore, we have a shift in the index. We need one level less of comprehension. Well, we need here one level less of comprehension than here. So there is a shift just for the countable case, and then if you can iterate this generalization for any transfinite level of the Boyle hierarchy, and you will have the same bond. So the shift is just due to the, let's say, the shift from the countable case to the incountable. Right. So this is the result I wanted to state. And now I would like to sketch as clearly, as helpful as possible, the proof of that result. So the idea is to define a pi04 and games that cannot be determined in a minimal model of KP2n. So before we wanted a pi03 and games that cannot be determined in L alpha n plus 1. But by generalizing this game, we found out that we need one more level, one more condition, so that it works. So that now pi04 n plus 1 is not provable, determinacy is not provable in L alpha 2 n plus 1. And so that's how we end up with this shit. But then we could ask, could we end up with a better game, more optimized, so that this the same kind of index works. But it turns out that we can save a quantifier in the proof of pi04 n determinacy compared to the proof in the countable case. And this way it proves that the adaptation of the proof, let's say, is optimal. As much optimal as the first result was. Right. So I still have 10 minutes. So I will sketch the behavior of sketch again. So the idea is to define a game Gn that has n pi03, well, okay. In that case, n pi04 condition, and we will take the difference of these conditions. We have the right form of player set. So one, it is a pi04 n game such that so before we played 0 or 1, whether we thought the property was true or false. Here we will play just sequence of 0 and 1, and according to the position of the 0 and 1, this will be the answer of each player, whether he thinks some enumeration of the formula of set theory are true or false, making so initially sequence of 0 and 1 correspond of a theory. Of the theory. Right? So if player one plays a sequence of 0 and 1 that correspond to the set of the numbers of theory of L alpha to N, he wins. Second, if player 2 plays or 1 does not, then 2 wins. So this means that inside L alpha 2N, we will have construct a game. Well, first KP2 N port, and then we will have construct a game that proves either for N determinacy to be wrong, because if one of if player 1 has a winning strategy to that game, and player 2 happen to play the set of Gödel's number of the theory of L2 alpha to N, sorry, then he has to play the theory of L alpha to N. And this means that you can compute the theory of the model inside the model from the winning strategy of one. So we will also
so I have to be time following, right? So what is the game, right? So in each step, like player 1 speaks, basically chooses one truth value of some sentence. I guess we can have the sentence with calling functions or something like this.
No, so you just take an enumeration of all formula of set theory.
Right. Oh, okay. I guess. Okay. Constructive case. I guess it doesn't matter. Calling functions or not. Right. Anyway.
Yeah, I think no.
Yeah. Okay. 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 Anyway. Okay. Okay. So So player 1 tries to play the theory, but what players?
So we want to end up with that. So player 2 is doing the same. They both play a theory, and since we
Okay. They kind of both.
So that's the goal. That's just the goal. Not explain everything yet.
Oh, okay. Well, but okay. What is the jingle? I still don't respond to the jingle. Okay, they both try to play this theory, but then it kind of who wins?
Yes. So in the end, player 1 will have the winning. Well, it depends on what.
No, but like okay. I mean, like this is what we kind of want to extract from
But
the
the
game.
idea is that if someone has a winning strategy, then it's possible to compute from this winning strategy the theory of L.
Okay. Okay. So it's not they're not like in the game they're not really playing the theory, but like basically
Yes.
then we will be able to show that any winning strategy is like.
Yes. So the
Okay.
theory becomes computable
Okay.
inside the model, and this is the contradiction.
Okay.
That task defined to be good. So this is the basic principle of this game. So just very quickly, yeah, can you raise? I think.
Yeah, but I think it's okay. I heard of this. I think proof at some point about the proof of dependence or parallelism. Like I think the general idea is more or less the same, right? So you kind of follow these things. So you kind of construct the game where with giving intelligence should be theory of some sufficiently large constructed.
Yeah, is that so?
No, I think kind of, at least like in broad terms, I think kind of it's the same strategies. For example, Friedman used for the proof of independence of parallel determinants.
No. It's not the same kind of proof.
Oh yeah.
So you were talking about Martin's proof?
No. I don't know. There is this Friedman theorem about independence of parallel determinacy from ZFC minus power set, or even like from from Zermel's theory, right? So, and I think kind of in very rough terms, it's kind of what he was doing. He was kind of constructing this game where you kind of play this level, essentially series of like sufficiently strong levels of constructible error.
So this is very similar to the early proof of Friedman that they get 3 minus power spectrum. Does not prove by the for determinacy. So the idea in the proof is that L alpha 2n is the only well-founded model of that theory. Well, of the theory plus the parallax is the minimal model, of course, because of most of the columns. If you have a well-founded model, you take most of the columns, and it's isomorphic.
No, I mean by this theory, you mean theory. This is KP2n, and there are no constructible models.
Yes. Okay. So they must play Tn, 2n, let's say, which is consists of a consistent complete extension to complete extension of Tn, which consists of KP2 and this P equals let's say
plus there are no smaller models.
Equals L alpha 2n, so it's a minimal level also, and
Okay.
so because of that, alpha 2n is the only well-founded model. And so all the point of the condition is to identify the ill-founded model.
Right.
Because with a pi0 condition, it is, well, actually Friedman first proves that for pi05, and Martin proves the same for pi04. And now we haven't, well, from Montalban and Chavez, we haven't had better. But so the idea is the same, because with a pi04 condition, it is easy to it is more easy to find out which of both models is ill-founded, and then to identify the winner following these conditions. But in Montalban and Chavez, we need to use an unification of pi03 formula. And here it is the same. So it is basically the same game, but more refined.
Right. No, but here I'm asking because I think kind of I'm not sure if people here actually even know this unrefined result anyway. So maybe like give general idea of how these things are done is better than kind of going to the intricacies connected to like your precise result. I'm not sure.
Well, yes. So main idea is for the very expensive. These things. But the main idea is to identify the well-founded model. And the reason why we need one extra condition in the countable case is that so we have these two models played by the two players. Let's call them N1, N1, and N2. And N2 is ill-founded. But the problem is that now the highest, so we can ask for them to be omega models. So in the countable case, the highest cardinal, because we play with minimal model, is omega. But in the uncountable case, the highest cardinal is omega 1. And so let's say that this is the ill-founded part of M2, who will lose the game because she will lose the game because she played an ill-founded model. Then omega 1, the omega 1 of this model could be in the ill-founded part, but also in the it could be in the common part. and we don't know, and we can ask explicitly to this highest cardinal to be in the common well-founded class. And it's for that reason that we need to control a bit what's happening with this high cardinal, and that we need to be sure that everything is going well at that point before doing the same game that Montalbano showed. So in a nutshell, it is the reason, but I think I will stop here because the rest is very technical and it's not a good idea to explain it when you're overlapping probably.
Okay.
But we can discuss more if you want.
Okay.
So thank you very much.
Yeah. We didn't have any questions. Okay, okay, so I think here, so you have kind of the semantical result, but what about reverse mathematical result? I mean, because
Yeah, right. So it's not exact bounds. Well, it's not an exact characterization. But now the goal would be in future research to tighten, at least tighten the bounds of these.
no, but I think it's okay. So with this kind of result, okay, there are two parts reverse mathematics. Okay, first you need to tighten this, right? So in the sense, like you need kind of here you have this kind of gap for this, right? But on the other hand, like there is a question of meta theory, I believe, right? So because actually, well, maybe it's not a real problem, but because okay, again, with the semantical methods, you don't really care about what is your meta theory, right? And so, but I don't know, maybe it's start to matter.
But what do you mean by only semantical result?
No. I mean, no. Okay, I mean, like your result is so basically that something happens or not happens in particular level of acceptable hierarchy, right? And I guess your meta theory is like GFC, really, or
Yes.
or you don't care, right?
Well, actually, the meta theory here can be a C0.
Oh, okay. So
It can be.
no, but like, okay, well, my problem is not a problem. Like, so my impression was some kind of subtlety here because, okay, so when you kind of making this game, playing this theory of something like whatever, L to M or whatever, right? It's kind of what makes it different whether you know that there actually exists well-founded model of this thing or not.
Yes.
Okay, I don't know.
Right, but that's the. Yeah. We don't really need the existence of well-founded model, I would say, because here we define the game formally, and if there exists a well-founded model and one of both players play it, then for sure he will force the other player to lose the game. But there are other ways to lose the game too.
Okay.
So
this is not a problem.
yeah, so the thing with games like that, when you define this kind of condition, is that one player can win the game in other ways, probably. Because the other player is not playing the more smart strategy against him. But here, the more smart strategy, we cannot define it because it would ask player 2 to play alpha 2n probably.
Okay, no, right. So basically the point is like, yeah, so what we actually need to prove in this analysis case, like, yeah, so basically, unless your strategy is basically picking this part of the same theory, like it's always a smart, better strategy.
Yeah, right.
Okay, no, but basically my question was, what was kind of meta theory for this kind of material? But you're saying that basically meta theory is AC0 already now.
Yeah, AC0 is.
Okay.
I have another question. Namely, you're working with a power set of omega. Is this what is going to happen when you iterate finally of the power set of the power set?
Right. So here, so remember this result of Martin with alpha plus 4. So if you have alpha for iterated power set, then alpha plus 4, while 0 alpha plus 4 determinacy is probable. And here you can also you could define well, okay, it's here. You could add iterated power set here. So if you add plus, say plus alpha here, and then you also add plus alpha.
Sorry. Why to the right, not to the left?
Also here. Sorry.
Sorry, no, but I'm concerned that you adding 4 is added to the left and not to the right, because before in the Martin result you had alpha plus 3 and alpha plus 4. And okay, no,
It was alpha plus 4, but one is not probable and one is probable.
No, I think it's probably it's actually strong. So because the point is like 4 plus alpha is the same as alpha is large enough.
Oh,
Yes. Yeah.
yes. Sorry. You're right.
Okay.
I thought it was.
Okay, I guess I have maybe some
And he.
like
There's a problem that alpha looks like
okay. Yeah. Anyway, yeah. So I think I have.
you should maybe just be careful about the limit here.
All right.
Well, it's in process to be written down, so when you write it down carefully, there's no problem. Let's say that alpha is finite, but it also iterate to the constraint of finite, because the proof can be attacked now, because now we have a way to handle these highest cardinal in the model. So now there's nothing bad can happen by generalizing.
So how much does it matter that we really deal with these games on bare space? Because again, so if the general technique, right? So this is like they really, and then they go to this games on kind of general tree spaces or something like this, right? So maybe you could just like relativize all these results. So when you kind of replace omega with some abstract set, and then like you have
yeah, right. You see, well, here we only play 0 and 1.
Yeah.
So we play technically in a contour space. But the thing is that when you reach the level delta 03,
yep,
then delta 03 determinacy in bare space is equivalent to delta 03.
No, but like sorry, no, but this is what my question.
In contour space.
No, sure.
But you mean
no, I mean like no, because I meant like dealing with this more abstractly, really, and like covering cases of spaces of higher cardinality. So because I mean, again, so if you're looking at kind of proof of Martin's theorem, right? So you really have reduction to this space of much larger cardinality.
Yes.
So then it kind of suggests that you may like it's reasonable to consider games in such spaces, and so maybe again, so just consider say series where instead of like considering games on omega, you have just absolute constants per space, and then you kind of looking for what kind of power set structure above this constant you need or something like this to prove determinant.
Well, you can play with, for example, games with real number moves.
Right.
But then, for example, if you want sigma 01 determinacy, you need a third order arithmetic.
Sure. No, but like sure. No, but like basically my question is how much basically do you like have direct analogs of these results or not really? So basically it would be the case like make a concrete question, right? So for example, consider this statement that for it's kind of a tree space X, you have pi, say, like pi 0 for determinacy, or I don't know what it says doing here. You consider like distance hierarchy of pi 0. Okay, so example, we have like nth level of distance hierarchy of pi 0 for space like this abstract tree space X. And then the question would be basically would it be possible to kind of to prove the statement in the say in the theory KPM plus power set of your space X exists.
Right. So it looks reasonable, but I didn't really look at it for now. I know that when you use games with real moves, when gaming counter space, where equivalent at the level delta 0,1 and sigma 0,1, for example, then it's no more equivalent. So new things are happening, but and namely determinacy. You don't need choice to prove that the determinacy of all games with real moves fail. It is not provable in ZF without axioms. Where when you only have games in pair space, then you need choice to construct pair set enough complicated so that it's not determined. But if you play in the real with real numbers, then you don't need choice. You don't need choice anymore because it's really.
So, but how fast does it happen? So, okay, so barrel games should still be returned, but then if you say, would it like fail on the levels of analytical hierarchy over of given space? Or?
I don't know about that too.
Okay,
but, I know about the station.
Okay.
But yeah, it's one of the direction where we could broaden this work.
Okay.
I have a final question. I was announcing this talk on Facebook, and I got a remark by Ken McAloon. He was asking about the strength of the borrow wage determinacy.
Oh, yeah, right.
Well, so he's interested in this. And so the point is, this is provable in second order arithmetic. The question is whether there's some time structure.
Yeah, I don't know much yet about borrow wage determinacy. It's one of the subjects I want to deepen.
So he might be interested.
Right. I was planning to tackle that too. Right. So, what is his name?
Ken McAloon?
Can make me.
Yeah, he's was quite active, let's say, 40 years ago.
All right.
Yes. But he knows lots of stuff. He knows lots of history.
Right. Yeah, determinacy is a very wide subject. So at least I hope you will have this message as a conclusion.
Okay.
Questions online?
Yeah, actually, it's true.
Vai, ci deve essere. Alak and Philip.
Okay.
Yeah. And myself.
Not for me.
Good.
You actually have a question.
No, he said not from me.
Okay.
Okay, then